Okay, so today we will get into actually doing some examples of our probability of multiple events. So, example one, let's consider this table that I've made that looks at maybe a class of students, a group of them that models their classes that they're taking. So we've got 10 students that take Spanish and Algebra 1, 9 that take Geometry and Spanish, 8 that take Algebra 1 and French, and 4 that take Geometry and French. There's a total of 31 students, a total of 13 that take Geometry, 18 that take Algebra 1, 19 that take Spanish, and 12 that take French. What is the probability a student is in Geometry or French? So this table kind of breaks this down a little bit nicely for us. We need to know potentially whether these are or are not mutually exclusive events. So can these two things happen at the same time? Can a student take Geometry and French? Yes, they can. There are 4 students taking both Geometry and French. So we can't just add the number of students in Geometry to the number of students in French and use that probability. We have to make sure we don't count any of them twice. So there is a total of 31 students here. So we want to know how many take either Geometry or French. So there are 9 students that take Geometry and Spanish. So they would count because they take Geometry. There are 8 students that take French and Algebra 1. They would count because they take French. And there are 4 students that take both Geometry and French. They do count. They do use the word or in this case, but if someone were to ask a student, do you take French or Geometry? A student that takes both would still answer yes. So we would say that there are 9 plus 8 plus 14 favorable outcomes, or however you'd like to use that here. So we've got 9 and 8 make 17, plus 4 is 21 out of 31. We could just leave our answer as that, or let's see, 21 out of 31 is about 67.74%. So there are 2 different ways that we could express this. 31 is a prime number, so this isn't going to simplify. So those are 2 correct versions of the answer. Keep in mind, if we were to do 13 and 12, because those are the totals for Geometry and French, we would get 25, not 21, because we would have accidentally counted these 4 students twice. So that is why it is important to consider the event that 2 things could be mutually exclusive or not. Okay. Example 2, Kentucky has won 5 of their 16 games. Kentucky basketball is not in a very good place right now, unfortunately. So we are saying if the likelihoods of winning each game are independent. So we're going to assume they're independent. This is probably not quite correct and that they're not all the same, but I think we'll get a good estimation of the likelihood still anyway. What is the probability Kentucky wins their final 8 games? So we're using experimental probability here. Each of these games would theoretically be different, but if we're just using the experimental probability, the likelihood that they win any individual game right now appears to be 5 out of 16. So since these are independent events, all we have to do is multiply the probability of each individual game to get the probability that they win all 8. So that would be 5 out of 16. The second game would be 5 out of 16. The third game would be 5 out of 16. The fourth, the fifth, the sixth, the seventh, and the 8th. So if we multiply all of these probabilities, we would theoretically get what it's supposed to be. Or better yet, we could say we're multiplying 5 out of 16 times itself 8 times. That's when exponents come in. 5/16 to the 8th power. It's not looking very good for Kentucky here. So that is a decimal. We're going to change this to about equal to and multiply this by 100 and say that they have about a 0.0009% chance of winning their remaining 8 games. Sad times for them. In other years, that might be possible. So now for our last example today, let's go and look at events that are explicitly dependent, that do depend on each other. So in example 3, suppose there are 6 red candies and 4 blue candies in a bag. When pulling 2 candies out of the bag, what is the probability they will both be blue? So these are dependent events because pulling the first one out changes the probability of the second one. So first, let's look at what's the probability that we pull a blue one out first. That is going to be, we've got 4 blue candies, and then there are 6 red, so there's a total of 10 here. So our first one is 4 out of 10, or 2/5. I know I can simplify that. So then let's say if that happens, what's the probability we pull a blue candy out again? It is no longer 4 out of 10 because while we're looking at those candies in there, let me demonstrate this a little bit just so we see it. So we've got 1, 2, 3, 4, 5, 6 red candies and 4 blue ones. 1, 2, 3, 4. So if we were to reach in and randomly pick one of these, right now the probability is 4 out of 10 that we get a blue one. But let's say we do pick a blue one out of there. The second time around, the probability of pulling a blue one out is slightly lower. It is not 4 out of 10 now, it is 3 out of 9. Because we've taken a blue candy out, which means we've taken a candy out. So both the numerator and the denominator change the second time around here. There are 3 blue candies left and 9 total candies left, which is a third. So the probability that we get blue for both of them, again, it comes from multiplying the individual probabilities, but we had to find them because they are dependent and therefore they weren't the same in this case. So that is 2/5 multiplied by 1/3, which is 2/15. And if I wanted to know what 2/15 was, 2 divided by 15 is about 13.3%. So that is a case of how you could handle 2 dependent probabilities.